Hello everyone. Welcome back to the channel. I am Sanket Singh. I'm working as a software engineer at Google. And this is going to be the first video of the 10x Engineer Bootcamp. If you don't know what is 10x Engineer Bootcamp, I would highly recommend you to first of all watch this particular video that is pinned here. In this particular bootcamp, we are going to learn programming from absolutely scratch. And when I say programming, then I definitely don't just mean data structures and algorithms. We are going to learn a lot of concepts of basic programming. Then we will take a deep dive in algorithms, data structures, and we will also try to do a lot of hands on software development. Right. We are also going to launch a bunch of lectures where you will actually learn how to do development in web as well as mobile by like yourself. You will be able to learn everything from scratch, and this is the first video of 10x engineer bootcamp, so I definitely require a huge amount of support from all of you guys, right? This series is definitely something that I've planned for a very long time, and most of the lectures of this series we have already recorded. At least for the algorithms and data structures part is almost everything is done, so you won't feel like that we are lagging behind or we are behind the schedule. You will see a very consistent display of lectures getting put out on this particular channel, right? So if you have not yet subscribed to the channel, this might be the correct time to subscribe it, and please do share it with all of your friends in your own college or maybe different colleges so that we can have maximum reach throughout the country, right? This lecture is something very special. I believe everyone must be already knowing about, I would say, number systems. You must already know what is binary, what is decimal. But this lecture is a bit special. I'm not just going to talk about what is binary number system, what is decimal number system, but actually I'm going to talk about what is a number system. Like how actually you give a thought process to a number system. For example, let's say in binary you just have two symbols, 0 and 1. You are able to do the counting. What if I give you a number system which is having seven unique symbols? How will you do the counting? And is this counting having any pattern, right? Like, is there any similarity between how do you do counting in different number systems? There is definitely a similarity that a lot of people miss, but we are not going to miss that. This is going to be one of the most exciting, I would say, video on programming concepts, definitely for all of you. I would highly recommend you to watch it around in 1.5x for the best experience possible. And without a further ado, let's just start and let's take a deep dive into number system. So before we move forward, I would like to tell you about algocamp.io. So if you are someone who is willing to learn programming from scratch in, let's say, Java or JavaScript, right? Or if you are someone who is preparing for their interviews, then algocamp.io can be one-stop solution for you, right? You can see on algocamp.io, there are a bunch of courses regarding data structures and algorithms in JavaScript. So let's say if you are a front-end engineer who is aspiring to become a front-end engineer and preparing for interviews where you will be asked questions in DSA and the main language that you use is JavaScript, then this can be a really good course for you. Apart from that, you can see there is a dedicated course on mastering Java with backend in Java in Spring Boot along with system design, right? You can see all of the concepts regarding basic Java, then data structures and algorithms in Java, and tons and tons of problem solving is actually present there. You can see more than 400 problems you are going to solve in this particular batch. There is going to be more than 300 hours of hybrid content. Some content will be coming recorded, some content will be coming live. You can see we are going to talk about all of the important data structures, including segment trees, heaps, graph algorithms, dynamic programming, all of the things. Apart from that, there will be additional computer science fundamentals like computer networks and database management system as well, right? Apart from that, there will be dedicated lectures on Spring Boot, that how you can actually make good backend applications with Spring Boot. And there are going to be more than 10 projects that you are going to do actually in this particular batch. You are also going to be introduced with low level design with different design patterns, as well as high level design where we will talk about problems like how you can design a system like Uber, or how you can design something like URL shortener and whatnot. You can see the price of the course is 4200, and this is something that we have kept very affordable. And in fact, if you will use the coupon code algocamp 500, you will get 500 instant off on this particular course. You can see the instructors for the course is Ria Bansal, who is actually a software engineer at Microsoft. She has previously worked with Flipkart. I'm also going to assist her in this particular course. So you can see the mentor side of the course is totally sorted. The price we have kept is very competitive, considering that you are going to learn data structures and algorithms. system design with design patterns and high level design, as well as backend development in Java. Right. So this is one power pack course that you can definitely opt for. So you can check out algocamp.io for more such interesting stuff. I have made a dedicated video on what you can expect with this Java course and overall in algocamp.io. You should definitely check out that. I will link all of the things in the description section below. So don't forget to actually check that out. And now let's just move forward with our current video. So guys, my feeling is that before you start any type of programming, before you actually start learning any programming language, there is a very important concept that you should always know, because programming is all about like problem solving, doing a bit of maths and everything, right? So it's always important to understand how the computer works and how the computer understands. So computer is a dumb machine, right? Computer doesn't understand a lot of things. You have to instruct the computer to do anything. For example, even if you have to turn on the computer, you have to manually go and press a switch to turn on the computer. That's the biggest disadvantage that the computers come with, that you have to instruct them, and you cannot instruct them in your English language like the way I am talking to. You cannot instruct your computer in the same way, in the same English language way, right? So how can you instruct a computer? The computer only understands binary. Why? It's an electronic system. Computer is a electronic system. Computers are electronic system, right? So they understand only current flow. They only understand one thing, whether there is a flow of current or there is no flow of current. So if there is a flow of current, if there is a flow of current, they consider it as a binary one. If there is no flow of current, if there is no flow of current, they consider it as zero, right? So any signal that you have to give to the computer, you have to give it in the form of binary, right? So you might have even heard about binary systems and everything. We are going to talk about that today, right? So computers only understand binaries. Computers understand binaries. Now, talking in binaries is going to be hard for us as humans, right? It's going to be hard for us as humans because we are well versed with languages like English, Hindi, German, Marathi, all of these languages that exist in different parts of the world. We are more comfortable in speaking that and understanding that. For example, if I'm going to talk to a computer, I cannot just talk in English to the computer and they will be able to understand. And neither I can talk in binary because understanding binary is very difficult for us because it takes a lot of time to process like what the binary expression is saying. So we cannot like just directly talk in terms of English. Computers cannot just directly understand English. They need binary. So what we have is we have programming languages. We have programming languages. So you can say that it's kind of like a interface that exists between us and the computers. For example, if I'm going to talk to a German person who knows German only, and I'm going to talk to them in English, they won't be able to understand a lot of English. But if I keep a translator and I somehow convey my message to the translator, and the translator will convey the message and convert my English message to German, then the German person will be able to understand, right? So people keep translators, right? So translator is also like an interface between or a layer between two people, that if they are not coming on a common ground and they don't know same language that they speak or understand, then the translator helps to modify things from the input and gives a relevant output, right? Same thing exists with programming languages. They are kind of like an interface that exists between us and the computers. We are going to communicate our things in programming language, whatever programming language, for example, C++, Java, Ruby, all of these programming languages, we are going to convey our message in. Now, it's the duty of these programming languages to convert whatever instructions we gave to the computers. There are different mechanism every language follows, right? We are going to discuss things around C++, so we will understand how exactly C++ conveys the message to the computers. But this is the basic understanding of programming language. If somebody asks what is programming language, it's like kind of like an interface using which we are able to communicate instructions to the computer. Programming language is not absolutely English or absolutely German. They have their own nuances. They have their own, I would say, set of rules and instructions. So we have to abide by that. We have to follow that, right? But before we actually get deep dive into programming language and like understand what is a programming language and how you can get your hands dirty on any programming language, I would like to make sure that just wait for a bit more while, and we are going to talk about something even, I would say, interesting and even important. Now, as I said, we know that computers only understand binaries, and binary is technically a number system, right? And we are also aware about one more number system, that is decimal number system, right? You write your numbers in 0, 1, 2, 3, 4, 5, 6, so on and so forth, like these kind of situations you have for writing your numbers, right? You can write something like 99, 104, 1600, something like this, right? This is your decimal number system. So how exactly numbers come into the picture, we have to understand that, because a lot of time during our problem solving and initial part, we are going to use the binary number system. So this question will keep clicking your mind, that why we have binaries like this, how do we count binaries, what are different things in binaries, so on and so forth. So I want to like spend some time in the initial days to in this initial part to actually make you well versed with number systems, where we are going to focus a lot on the binary number system and the decimal number system, and then we will try to figure out a lot of things around them. And later we will try to, when we will be having some knowledge of programming languages, we will be able to even interconvert different number systems here and there. So a lot of things are going to be interesting for you. So we are going to today start with number systems. Number system. I hope this point is making sense, that why we are actually starting with this topic. Now let's start talking about number system, right? So like if I ask you that, hey, please write 44, please write 44, then you're going to write an expression like this, 44. If I ask you to write 13, then you're going to write an expression like this, right? So in our early school days, we are taught a number system called as decimal number system, right? If you ask me what is a number system, it's like how the numbers are going to be managed. Number system defines how the numbers are going to be counted, what are the symbols, what are the unique symbols you have in the system, and how you are going to do the counting. For example, in decimal number system, why do we call it as a decimal number system? Because we have 10. Decimal stands for like 10. So we have 10 unique symbols in decimal number system. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These are the 10 symbols, 10 unique symbols of decimal number system. Whatever numbers we are building, every number is built using these 10 symbols only, right? For example, if you have to write 44, so you take this symbol of 4 and like write it twice, something like that. So whatever numbers you are going to build, whether whether it is a number in the order of 10 raised power 5, 10 raised power 16, anything, you can build it with these 10 symbols, right? Okay. But have you ever asked a question? Have you ever asked a question that, okay, if we start the counting from 0, then you go for 0 to 1, then 2, then 3, 4, 5, 6, 7, 8, 9. After 9, to represent 10, why do we write 10 like this? Like 1, 0. What is the logic of 1, 0? Like, why not something else? Why not 0, 1 we are writing? Or why not 0, 2 we are writing? Or something like that, right? This should be our first question that should come to your mind. Like, why we are writing 13 like this only? Is there a logic, or just we built some set of rules? Because there are two things always. There are two things always, that sometimes people build things out of logic. Sometimes people build things out of conventions or rules, right? So is this just like a general rule that has no sense at all? Or is there some logic written behind that? If you have to count after like 9, then there is some logic that you write 10 like this or 11 like this. And the question exists that if there is a logic, if by some logic we are writing this, then whether that logic applies to other number systems. So there are other number system also. For example, binary number system. In binary number system, you only have two symbols, 0 and 1. There is like octal number system. In octal number system, you only have 8 symbols: 0, 1, 2, 3, 4, 5, 6, 7. There is hexadecimal number system. So you have 16 symbols: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, right? 10, 11, 12, 13, 14, 15, right? 16. I guess we have 10, 11, 9, 10, 11, 12, 13, 14, 15. I guess this much will be there. A, B, C, D, E, F, right? So we have 16 unique symbols, right? So now, if you have 16 unique symbols, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A stands for 10, B stands for 11, 12, 13, 14, 15. Now, how do you write 16? How you are going to represent 16? That should be a question, right? Are you going to represent 16 like this? Just like how you do in decimal number system? No, this is not how we represent 16, right? So actually, how we do this counting, how all of this came into the picture. When you are going to learn data structures and algorithms, it's all about problem solving and logic building. And all of this somehow, somewhere revolves around numbers. So why not start your problem solving journey? Why not start your logic building journey with actually understanding how decimals work, how number system works, and then slowly and steadily progress, right? So today we are going to actually decipher the logic that how exactly counting is done. Like after this symbol 7, how do you write 8 in octal? What is the logic there? How do you write 16 here? 17, 18. Is it going to be same as decimal number system or what? We're going to talk about that, right? So first thing is these number systems, whatever we are learning, these are quite modern, right? If you go for very early days of human race, when we definitely didn't know how to speak and how to properly cook food and everything, do you think during that ancient age we were aware about decimal number systems to do the counting or something? No, right? At that point of time, let's say if somebody is going to give someone 5 wooden sticks, so how they used to represent the things? They were not having these modern symbols. The ancient people, they were not having these modern symbols. How they used to represent anything? Let's say if somebody wants to give someone 5 wooden sticks, that they are demanding 5 wooden sticks. So to represent this quantity 5, they used to draw lines: 1, 2, 3, 4, 5. Right? This is how they used to communicate. That if there are 5 lines, then someone is asking for a quantity of 5. If let's say 7, right? Or then slowly and steadily people developed few more things, that how about you also put a cut like 1, 2, 3, 4, 5, then 6, 7, 8, 9, 10, something like this. So these kind of behaviors people developed, right? And then, like, instead of this, like for writing 5 wooden stick, you have to like draw 5 lines. Think about, if you have to write 500 wooden sticks, then how many lines we need to draw? It was very cumbersome. But when they came up with a logic like this, that okay, we can represent 5 like this, right? So at least some effort is saved here, right? So what they saw, that there is a good amount of sense in actually building symbols. There's a good sense in actually building symbols rather than just having a straight line to represent one quantity. We can maybe have different symbols, because different symbols will be able to reduce the amount of work that we have to do. For example, in using these straight lines, if I have to represent 1005, it's going to be a huge task for me to write, and I might also lose the context that how many lines I have already drawn, right? But if I write 1005 in front of you, you immediately understand, okay, you want 1005 quantity of something, right? So see, using 4 characters we are able to do the same thing, for which we might need a hell lot more. So early in earlier days, people used to like use just these straight lines and then actually get the things here, right? Okay. Slowly and steadily, different number systems start coming into the picture. Different number systems start coming into the picture. For example, the Roman number system, right? The Romans came into the picture and they also gave us some symbols, right? So what Romans actually did, Romans actually took very big numbers or higher numbers with a different symbol. For example, in Roman numbers, we were having 5 as the symbol V, right? They use the symbol of V to represent 5. Now, they put some logic here that if you put one stick behind it, it will become 4. If it will be something like this, it will become 6, and so on and so forth. Using this, what they realized was if they have to represent 6, they can represent 6 like this instead of representing 6 like this, right? So it was way more easier to represent 6 like this with very less characters involved, right? So what they actually did, they kept on building symbols. For example, for 10, they built something like X, right? And slowly and steadily, what they realized is if they have unique symbols for different quantities, then their task is very much reduced. All they have to build is some kind of logic around it. Later down the line, people came up with symbols like these: decimal systems, binary system, and everything. And now, having these number systems, we have a common logic around it. It's not like just a random thing that you write 13 like this in decimal system. No, there's a proper logic that exists in every number system, which is common across the number system, that we use in order to actually build the things. So let me talk about it. So let's say if you are counting things in decimal, how do you even write it? You write 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is how you write the first 10 symbols. Now the best part about decimal number system is you have 10 unique symbols. So at least the first 10 numbers you can very easily count, right? If I have to say give me 5 candies, you just write the symbol 5. You don't have to make any effort, right? Because you have a unique symbol to represent 5. You have a unique symbol to represent 6. You have a unique symbol to represent 7. You have a unique symbol to represent 8. And you have a unique symbol to represent 9. But what if I want to get a quantity more than 9? Do you have a symbol for it in decimal systems? No, we don't have a symbol for it. So we somehow have to reuse the symbols. How do you reuse the symbol? As a very straightforward logic. You start repeating the numbers. See, you used 0 uniquely, 1 uniquely, 2 uniquely, 3 uniquely, so on and so forth, 9 uniquely. And then you start repeating the numbers, that you write something like 0, 1. This is the representation of 10. And why do you write it like this? Because the logic is repeat 0, or let me write it here. The logic is repetition of 0 first time. That you are first time repeating 0, right? Initially when you were having 0, it was to represent a quantity 0. But now because we have exhausted the symbol, now what we are going to do, we are going to reuse the symbols. So writing 1, 0 means we are repeating 0 once. This is the first time we are repeating 0. If I write the next symbol, let's say if I write the next symbol in front of you, we have 1, 1. That means we are repeating 1 for the first time. Repeating 1 for first time. Then you have 1, 2. That is, you are repeating the symbol 2 first time, right? See, there was only one representation of 2. Now you are representing 2 for the first time, or repeating 2 for the first time. Then you are repeating. One second. Then you are repeating 3 for the first time. Then you are repeating 4 for the first time. Then you are repeating 5 for the first time, 6 for the first time, 7 for the first time, 8 for the first time, 9 for the first time. Now you are done with 19, and you have again exhausted the symbols, that you have repeated everything one time. Now what? Now you say, to represent the next set of numbers, I am going to repeat 0 again. So this is the second repetition of 2, second repetition of 0. Second repetition of 0. So you are going to represent 0 and you are going to repeat 0 the second time. Then you repeat 1 for the second time. You repeat 2 for the second time. You repeat 3 for the second time. You repeat 4 for the second time. So on and so forth. You repeat 9 for the second time. And now you have repeated everything 2 times. Now you are going to repeat 0, 3 the third time. Repeat 1 for the third time. Repeat 2 for the third time. Repeat 3 for the third time. Repeat 4 for the third time. Repeat 9 for the third time. And so on and so forth. This is how you actually do. And later you come up with something like 98, that is you are representing 8 for the ninth time. 99, now you have represented 99 because you are repeating 9 for the ninth time. Now what after 99? What do we do after 99? After 99, you have to repeat 0 for the 10th time. You have to repeat 0 for the 10th time. And how do you represent 10? You represent 10 like this. So you just prepend 10 like this. So you are repeating 0 for the 10th time. Then you are repeating 1 for the 10th time. Then you are repeating 2 for the 10th time, so on and so forth. And that's how you build number systems. That's how you build number system. Now you might feel that, okay, sir, this is a made up logic from you for decimal number system. I am going to give you my word. It's not like that. Let's see for binary systems. Okay. Same logic we are going to apply for binary system. So in binary system, you just have two symbols, 0 and 1. That's it. These are the two symbols, 0 and 1. Now you have exhausted all of your symbols available, unique symbols available. Now how do you write 2 here? So you have to repeat 0 for the first time. So one time you are going to repeat 0, so you write 1 0. Okay. How do you write 3? You have to repeat 1 for the first time. And that's it. You have repeated all the unique character first time. If you have to represent 4, then you have to repeat 0 for the second time. How do you represent 2 or the second value? It is as 1 0. Then 5. You have to repeat 1 for the second time. Now you have repeated 0 and 1 for the second time. How do you represent 6? You have to represent 6 as the repetition of 0 third time. What is 3? 1 1. How do you represent 7? You have to repeat 1 for the third time. How do you represent 8? You repeat 0 for the fourth time. How do you represent 4? 1 0 0. How do you represent 9? You have to repeat 1 for the fourth time. And so on and so forth. This is how actually counting is done. So if I actually show you the list of, let's say, hexadecimal numbers. Okay. So let me show you the table of hexadecimal numbers. Right. 1 second. And technically we have the list of all of the major number systems. So if you carefully see here, we have decimal, hexadecimal and binary. Okay. So up till 15 you were having unique characters for hexadecimal. C. If you want to represent 0 in hexadecimal, you have 0. If you want to represent 1 in hexadecimal, you have 1, 2, 3, 4. Up till 9 you have unique characters. Now the best part about hexadecimal is you have a unique character for A. Sorry, you have a unique character for 10 also, that is A. You have a unique character for 11 also, that is B. So you don't have to repeat anything. You have a unique character for 12, that is C. You have a unique character for 13, that is D. You have a unique character for 14, that is E. And you have a unique character for 15, that is F. Now you have exhausted all of your unique characters. Can I say that? See, you have exhausted all of your unique characters up till F. Now you have to do the repetition. So you are going to repeat 0 for the first time and see how 16 is represented. Repeat 0 for the first time. Repeat 1 for the first time. Repeat 2 for the first time. Repeat 3 for the first time. So on and so forth. Then repeat A for the first time. Repeat B for the first time. Repeat C for the first time. So on and so forth. Repeat F for the first time. Now you have repeated all of the characters first time. Now start repeating them the second time. Start repeating 1 for the second time. Start repeating 2 for the second time. Start repeating 3 for the second time, and so on and so forth. See, this is how counting is done. So in decimal, something which is 39, it comes as 27 in hexadecimal, because you are repeating 7 for the second time, and this is the position when you have to do this, because you only have 16 unique characters. So that's what I'm saying. Same thing for binary. In binary, you have just two unique characters. 0 and 1, right? Now, once you have exhausted these two unique characters, then you will start repeating the characters. You will repeat 0 for the first time. How do you represent the quantity 1 or first? You represent it with this symbol 1, right? So you're repeating 0 for the first time. You are repeating then 1 for the first time. and then you have repeated every unique symbol for the first time, right? You have repeated every unique symbol for the first time, right? Now you are going to repeat 0 for the second time. You're going to repeat 0 for the second time. See, repeat 0 for the second time. And how do you represent the quantity second, or how do you represent the quantity 2? You have already done that task. You have already represent 2 like 1 0. So you have to represent the repetition of 0 the second time. You just prepend 1 0 behind it. Then you have to repeat 1 for the second time. Then you have to repeat 0 for the third time. How do you represent the quantity third? Like this. Then you represent repetition of 1 for the third time. Then repeat 0 for the fourth time. See, fourth time. Repeat 1 for the fourth time, and so on and so forth. And the same logic applies to all the other number systems: octal, hexadecimal, decimal, everything. You can just see here, right? Because it could have been the logic, right? That once they exhausted f with 15, they could have represented 16 like 1 6 only. But why are they representing 16 like 1 0 in hexadecimal? Because you are repeating 0 for the first time, then you are repeating 1 for the first time, then you are repeating 2 for the first time. This is how actually things work in counting, and this is how actually counting of number systems work. So if you see this quite an ancient number system, if you see this quite an ancient number system, you will find a similar logic here. They have some unique symbols up till this quantity 10, and they start repeating. See, they start repeating things. So once they have this, they somehow start the repetition process. See, somehow they repeat, somehow they are repeating. Now they are repeating this. Now they are repeating. See, this character 6 was there, and they are repeating it one more time and doing similar things. So they have some sense of repetition, although their repetition is a bit different than modern repetitions, because for repeating for the first time, they are using this symbol, which was technically 10. They are not using 1, but they have some sense of repetition. Repetition is the core logic behind everything, right? Repetition is the core logic behind everything. In all of the number system, they have to prepare some logic of repeating the symbols. In our modern octal, hexadecimal, and decimal and binary number system, we have a common repetition situation, but few number system might also differ, which are like quite ancient, or like which were used way before. They might even use a different logic. Make sense, everyone? So this is the new question in front of you, right? You have to write the first 20 numbers with a new number system. So let's say we are developing a new number system, and in this number system, we are only going to have 5 unique characters. These are the 5 unique characters: 0, 1, 2, 3, 4. Only we have only 5 unique characters, and you have to represent the first 20, or let's say first 25 numbers using only these characters. How you can do it? Take out a pen and a paper and try to write it, and then we are going to pause here a bit, and then we are going to actually see the solution for it. Okay, so let's solve this question. How do you solve it? It's going to be easy. First of all, use all the unique symbols. So 0, 1, 2, 3, 4, these symbols are going to be used. Now you have exhausted everything. So to represent 5, you are going to repeat 0 for the first time, then repeat 1 for the first time, repeat 2 for the first time, 3 for the first time, and 4 for the first time. Then you have to repeat 0 for the second time, 1 for the second time, 2 for the second time, 3 for the second time, 4 for the second time, and so on and so forth. This is how you're going to write your numbers with the number system, which is having only 5 unique symbols. And that's it. As simple as that, right? So I hope the overall logic around how exactly basic number systems work is clear to everyone. Now we are actually going to shift our focus. We are going to actually see the majority of things around binary number systems. That what are binary number systems, and how exactly binary number systems come into the picture. What are the different situations and different properties that exist with binary number systems, because binary is going to be one of the most crucial observations that we are going to do, right? So let's talk about binary number system. Binary system. In binary system, you just have got 2 unique symbols, 0 and 1. Whatever counting you have to do, you have to do with these 2 unique symbols only, right? So if I write binary numbers, here I am writing decimal, and here I will write binary. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's say if I want to write till 12, then you initially you have to just use 0 for the zeroth time, because it's like the unique representation, and then 1. So if you have exhausted all your unique symbols, then you repeat 0 for the first time, then you repeat 1 for the first time, then you repeat 0 for the second time, then you repeat 1 for the second time, then you repeat 0 for the third time, and then you repeat 1 for the third time, then you repeat 0 for the fourth time, and then you repeat 1 for the fourth time, then you repeat 0 for the fifth time and 1 for the fifth time, and then you repeat 0 for the sixth time. This is how you're going to write the binary number system, right? So the logic still exists here. But the best part about binary number system is binary number system possess a lot of hidden qualities. There are a lot of hidden situations or hidden properties that binary system number systems actually possess. And these are going to be extremely very interesting. For example, if you just carefully see, let me just copy paste this. Let me just copy paste this. Paste it here. Okay. Now, if you just take a look at the last bit of all the binary numbers, last bit of all the binary numbers, right? Just take a look at the last bit, right? So if you don't know about what is a bit, so bit is going to be the smallest unique representation of a character in the binary, right? So I hope you guys know about bit, nibble, byte, right? One byte has got 8 bits, things like this, right? So if you just see the last bit, then whenever you have a even number, even number, even number, again a even number, again a even number, and again an even number, all of the even numbers have got a 0 at their last bit. All the even numbers have got a 0 at their last bit. Can I say that? Every time whenever you are going to have an even number, the last bit of the binary is always going to be 0. Last bit of an even number in binary is always 0, right? So if I ask you to detect whether the number is even or odd, one logic is, let's say if I give you 44, you try to divide 44 with 2. If 2 completely divides 44, that means it is an even number. But there is one more way. If somehow somewhat you can detect what is the last bit of 44 and whether that bit is 0 or not. If the bit is 0, then 44 is going to be an even number. So this kind of logic building we can do. And similarly, if you take a look at odd numbers, so this is odd, this is odd, this is odd, this is odd again, this is odd again, this is odd again, and so on and so forth. So all the last bits of odd numbers are 1. See, last bit of every odd number is 1. Can I say that? So last bit of an odd number in binary is always 1, right? So the last bit of the binary is always and always 1. That's the best representation that you can have for even odd numbers, right? So like, that's the beauty of binary numbers. In the binary representation, you have got hidden details. You have to take a look at those hidden details, and then you are going to clarify a lot of concepts for yourself, right? Okay. Now let's take a look at few more things, few more, I would say, observations, right? Now if I specifically highlight few numbers, let me specifically highlight few numbers like this, like this, like this, like this, right? So if you carefully see, whatever numbers I have highlighted, these are powers of 2. These are powers of 2. So what is 1? Can I write 1 as 2 raised to the power 0? What is 2? 2 raised to the power 1. What is 4? 2 raised to the power 2. What is 8? 2 raised to the power 3, and so on. And if you carefully see, in every power of 2, if the power of 2 is 0, you have 1 and there is no 0 following it. If you have 2 raised to the power 1, then you have written a binary 1 and then there is 1 0 that follows it. If you have written 2 raised to the power 2, then you will write 1 and then 2 zeros that follows it. Then 2 raised to the power 3 is 1 and then after 1 you have 3 zeros that follow it, and so on and so forth. Right? So in binary, we can write 2 raised to the power n by writing a 1 followed by n zeros. For example, 1, then 0, 0, 0, 0, so on and so forth, 0, and these zeros are going to be n times. So this is how you can represent 2 raised to the power n at any point of time in binary, right? And it's going to be a pattern. Whenever you see 1 followed by a lot of zeros, it's always going to be a power of 2. If you have 2 raised to the power 0, that means 1 followed by no zeros. If you have 2 raised to the power 1, 1 followed by 1 0. If you have 2 raised to the power 2, 1 followed by 2 zeros. If you have 2 raised to the power 3, 1 followed by 3 zeros, and so on and so forth. So this is like one more observation that you can get from binary number systems. Now let's start observing few more things. Around binary numbers. So now let me highlight these numbers, like let's say 7, or let's say 3, right? Or let's say 1. So if you carefully see, these numbers are 2 raised to the power 3 minus 1, 2 raised to the power 2 minus 1, 2 raised to the power 1 minus 1, and technically, yep, something like this, right? So whenever you have anything like, whenever we have 2 raised to the power n minus 1, then how do you represent it? You represent it by all ones. See, 2 raised to the power 1 minus 1 is single occurrence of 1. 2 raised to the power 2 minus 1 is double occurrence of 1. 2 raised to the power 3 minus 1 is triple occurrence of 1. So whenever we have 2 raised to the power n minus 1, we can represent it as n occurrences of 1. That's it, right? So this is going to be like one more very significant observation that we can make. So actually, one very simple thing that you have to ensure is, this is 2 raised to the power 1. This 2 is 2 raised to the power 1. And whenever we have to represent 2 raised to the power n minus 1, so let's say n is equals to 1, so 2 raised to the power 1 minus 1, you represent it with all ones, right? 1 can be also represented as 2 raised to the power 0. This is also something you can do. But if you see 2 raised to the power 0 minus 1 is all 0. So this thing exists for n greater than or equal to 1, right? Because for 2 raised to the power 0 minus 1, you have a binary 0. So you are not representing 2 raised to the power 0 minus 1 with all repetition of 1, you are instead representing it as 0. So this pattern doesn't work here. Otherwise, everywhere this pattern will work. For example, if I have to write 15, 15 is 2 raised to the power 4 minus 1. So we will be representing 15 as 1, 1, 1, 1. This is the binary of 15. I can by default say without even calculating it. Anyone having any doubts? Okay. So now let's observe one more thing. Right? So if you take any even number, for example, let's say we take 10. So let's say 10. The binary of 10 is 1, 0, 1, 0. If you have to calculate 10 by 2, that is division of 10 by 2, then all you have to do is just delete the last bit of 10 and you will get the value of 10 by 2. Can you see? 5 is 101, and if you just delete the last bit of 10, you get 101. And this works for every number. Let's say if you have 12, Binary of 12 bit 1100. If you delete the last bit, then you get 12 by 2, which is what? 6110. So see, the binary of 110 is 6. So for any even number, if we remove the last bit, we get number by 2, right? For example, let's see, if you have 6 and you remove the last bit, you get 1 1. What is 6 by 2? That is 3. If you have, let's say, 8, if you remove the last bit, 8 by 2 is 4, you get 100, and 100 is 4. Can I say that? And a similar thing works for odd number, but with a very small tweak. If let's say you have 9, 9 is 1001. What is the integer part of 9 by 2? 9 by 2 is 4.5. What is the integer part of 4.5? Can I say 4? So for odd numbers, if you delete the last bit, you get the integer part of number by 2. See, you get the integer part of number by 2. Let's take one more example. Let's take 7. Right, 7 is 111. What is integer part of 7 by 2? It is 3, because 7 by 2 is 3.5. What is the integer part of 3.5? 3. And can I say, if you delete the last bit, you get a 3. So let me write it. For an odd number, if you delete the last bit, you get integer part of number by 2, right? That's the essence of having these divisions. And as a counterpart, if you technically see, if like for this division, if I give you a counterpart, let's say you have any number 5. What is 5 into 2? What is 5 into 2? It is 10, right? What is the binary of 10? 101 and followed by a 0. Let's take one more example. Let's take 3. What is 3 into 2? It is 6. Binary of 3 is 1 1. If I append a 0, it gives you binary of 6, right? Let's take some number like 6. What is 6 into 2? 12. What is the binary of 6? 110. If I append a 0 in front of it, it gives me 12, right? So at the last, if you have a number and you append a 0 at the end of it, you will get number into 2. Can I say that? If you append a 0 at the end of it, you will get a number into 2. Can I say that? You can take any number. So let's say, let me write few more numbers. 12, 13, 14, 15. So we repeat 0 for this time, then we repeat 1, then repeat 0 for the 7th time, and then repeat 1 for the 7th time. Okay. Now if you do 7 into 2, 7 into 2 is what? 14. Binary of 7 is 111. If you append a 2, you get a 14, right? So if we append 0 at the last of the binary of any number, we get number into 2, right? For example, 7 is 111. 7 into 2 is 14. So if you do 111 followed by a 0, this is the binary of 14. So see how many different patterns binary numbers possess. With few observation, you are able to do a lot of things. And later down in the course also, we are going to see few questions where we will require the intervention of binary numbers, and we will observe few more patterns that these binary numbers possess. And actually we will be able to solve a lot of different type of and lot of different variety of questions using these binary numbers. So number systems are amazing. Number systems is not just a very simple thing, and number system is not a very complex thing. They are simply amazing. They have a lot of hidden details inside them. We can use the power of these numbers and the representation of numbers, actually solving a lot of real life problems. That's what binary number systems are. So, I hope you guys really liked the lecture. If yes, then please feel free to drop your comments in the comment section below. Right? Any suggestions, any doubt that you have, I would be happy to cater. I already know that a lot of fellow creators of mine are also making content on data structures and algorithms, and I highly appreciate that. The more similar content we are able to put on YouTube, the better diversity we will be having throughout the whole community, and better choices you guys will be having. I'm trying to make sure that the whole series in English so that we can reach out to maximum people. But definitely you will see that there are some fellow creators who are also making the whole algorithmic and data structure series in Hindi. So do definitely check them out as well if you find any difficulty. Anything that you feel like we can improve, I would be um, definitely willing to improve on that. And if you have not yet checked out algocam.io, please do check out algocam.io. We are going to launch some very cool live, hybrid, as well as fully recorded courses there. It takes a lot of time to prepare such quality content, including assignments, having peer support for all of you, maintaining a private Discord group where people can actually do the discussion, share a lot of resources within each other. So definitely, if you are willing to learn something that we are already offering at algocamp.io, do check it out. And we are going to meet soon in the next set of lectures. Till then, take care, guys. Bye bye. I am Sanket Singh, signing off.